Okay, so this is kind of moving us into the part where we talk about real world applications and we ask you to take what we've been working on and apply it to a real world situation. And the example I'm going to do in the video really isn't very complicated. We're going to get to more complicated ones during class, I think. But first, I just want to make sure that we know the difference between an exponential function and a power function, as well as a different form that you might use for an exponential function that might be useful. So an exponential function is y equals ab to the x, and that's where a and b are constants. So we're looking at numbers there and the exponent to be a variable. Okay, and we're only really talking about exponential functions where b is greater than 0. So the growth rate needs to be greater than 0. We're not using negative growth rates. And then a power function, in contrast, is where maybe the coefficient and the variable are constants, but the base or the growth rate is a variable. And I'm going to show you here in a little bit kind of what the difference is between those two. But basically that's the difference here. So in point ratio form, that's where we know it's an exponential curve, so it's an exponential function like the one above here. And we know a point that it passes through, and we know that the ratio for values of x that differ by 1, the point ratio form is y equals y1 times b to the x minus x1. So the only important part is that the ratio can't be between any of them. So for example, let's say we knew the point 1, 10, and then we knew that the next point after that was like 5 and 500. We couldn't find the ratio between these two because of exponential growth. That's pretty impossible to do. So only for x values that differ by 1. So we could find if we had an x of 1 and an x of 2 and we knew here, then we could find the ratio. We knew the ratio that the growth rate is times 2. Okay, so that's what that means when it just says you have to use x values that differ by 1. Okay, so I have an example here. An exponential function is similar to this one. This first one, the red one, is showing exponential growth. That's where the base is known, the growth rate is known, and we just are looking at a variable of x in the exponent. And then the blue one is, the blue function is a power function, meaning we know the power and we don't know the base. And so that's like our parabola, or for example, you could do it to the third power as well. That's a power function right there. Whereas this red line here, that would be an exponential function. So just a difference in those graphs and kind of something to be aware of between the two. All right, so Rita wants to deposit $500 into a savings account so that its doubling time will be 8 years. What annual percentage rate is necessary for this to happen? So she has $500, so if I'm thinking about my general form, I know that's like if I'm looking at y equals a b to the x, I know that the starting value is a, so that's where that's going to go in my equation. And I don't know b, I don't know the growth rate. We want to know the annual percentage rate. So I'm going to do 1 plus r. We're looking for that number there. I don't have to worry about dividing it by anything because it's compounded annually, so I don't need to divide out the percentage rate. And then I want to know how much time it's going to take to double. Oh no, wait, sorry. I want to know how much the rate needs to be so that after 8 years the account is doubled. So I put the 8 in the exponent because that's not a variable. We want it to be 8 years. In an exponential growth, this is often time. Let me get those written in there. I think this is something we've worked on before, just want to make sure that you understood here. And I'm doubling it, so I guess I know that the amount that I want in the account is $1,000. Okay, so I have this equation set up. I'll divide by 500. Now I need to get rid of that exponent, so I'm going to take everything to the 1/8 power. So I have 2 to the 1/8 equals 1 plus r. And then subtract 1, and I've got my rate. 2 to the 1/8 minus 1, which equals, did that already on my calculator, 0.09. So if I'm changing that back into a percentage rate, I'm going to say 9% approximately. All right, so like I said, pretty basic, pretty simple setup there, but effective and kind of just to get you started, and then we're going to work on more applications in class. You don't need to do any before class problem before you come. Yep, that's the only one I've got, so I'll see you soon.